Have you ever really stopped to think about how computers, well, think? It's not with words or feelings, but with a language of pure logic, a language built from the simplest idea imaginable. It's the language that runs everything from your phone to the entire internet, and today we're going to decode it together. So that's the big question, right? How can a machine that basically only understands on and off, like a simple light switch, build our entire complex digital world? From streaming movies to crazy advanced AI, it all boils down to this. And the answer? Well, it's actually pretty brilliant. To get it, we've got to start at the very beginning, with the absolute fundamental building block of all digital information. Let's call it the language of switches. And that building block is the bit. A bit is the smallest, most basic piece of information a computer can handle. Seriously, just think of a single light switch. It can be off, we call that a 0, or it can be on, which we call a 1. And that's it. Simple, right? But the magic isn't in one switch. It's what happens when you line up millions and billions of them. See, a single bit by itself can't do much. It's like having a language with only 2 words. So computers group them together. And the standard group size is a byte, which is just a little string of 8 bits. Think of it as the first real word in the computer's entire vocabulary. And this is where things get really interesting. With just 8 of those simple on or off switches, you suddenly get an explosion of possibilities, 256 unique combinations to be exact. And that is the breakthrough. By giving each of those patterns a specific meaning, computers can suddenly represent complex stuff like numbers, letters, and even the individual colors in a picture on your screen. So how do we actually translate our numbers into binary? Well, there's this really clever math trick. You just keep dividing your number by 2, over and over again. And all you have to do is keep track of the remainder each time, which is always going to be either a 1 or a 0. It's a super systematic way to convert any number we use into the computer's native tongue. Then you just take those remainders you collected, read them in reverse order, and boom, there you have it. The number 123 in our world becomes 111011 in the computer's world. So we successfully translated a positive number. But what about negative numbers? And that brings us to our next big hurdle. I mean, it's one thing to count things, but how does a computer understand something like debt or a temperature that's below 0? How do you represent negative when all you have to work with are 1s and 0s? Here's the thing, right? We can't just stick a little minus sign in front of the binary code. That symbol just doesn't exist in the world of bits. We have to find a clever way to say this number is negative using only the 1s and 0s we already have. So, how on earth would you solve that? Okay, so the first idea that probably pops into your head is the most straightforward one. Why don't we just set aside one of our bits, let's say the very first one on the left, to be our sign indicator? If it's a 0, the number's positive. If it's a 1, the number's negative. And the rest of the bits can just represent the value of the number. Seems totally logical, right? But it's a trap. This simple idea has 2 killer flaws. First, it creates 2 different ways to write the number 0, a positive 0 and a negative 0. That's just weird and wastes one of our precious patterns. But even worse, basic math just completely breaks. If you try to add 5 and negative 3 using this system, you get negative 8, which is obviously very, very wrong. This whole idea, it's a complete dead end. So if the simple way is a total bust, what do computers actually do? Well, let me introduce you to the hero of our story, a brilliantly clever system called 2's complement. And this is the standard that pretty much every single computer uses today. You know, the best way to get your head around 2's complement is to think of an odometer in an old car. As you drive, the numbers go up and up and up. But what happens when you hit the highest possible number, like 99,999,999? It rolls over back to all zeros. Well, 2's complement does something similar. When you count past the highest positive number, the bit patterns roll over and just become the most negative numbers. It's a continuous loop. So check this out. See how it works? The patterns that start with a 0, those are your positive numbers, just like you'd expect. But watch what happens the second that first bit flips to a 1. The pattern that should be the next highest number instead becomes -1. This one clever flip creates this beautiful, seamless range of numbers, elegantly connecting the positive and negative worlds. And this is why it's such a hero. Suddenly, all our problems just disappear. There's only one way to write 0, no more confusion. And the best part? Get this, regular binary addition now works perfectly, even when you're mixing positive and negative numbers. This means the computer's processor doesn't need a whole separate, complicated piece of hardware just for subtraction. It's an unbelievably elegant solution that's a huge part of what makes modern computers so blazing fast. Okay, we've totally nailed whole numbers, both positive and negative. But, the real world is way messier than that. It's full of fractions, decimals, and the absolutely gigantic numbers you see in science. How do we possibly represent that infinite range of possibilities? To crack this problem, computers actually borrow a trick that you probably remember from a science class: scientific notation. Instead of writing out some massive number with a ton of zeros, you just write the important digits, that's the mantissa, and then you make a little note of how many places to move the decimal point, that's the exponent. It's a super compact way to handle a huge range of numbers. And computers do pretty much the exact same thing, just in binary. It's a system called floating point representation. Every single one of these numbers gets broken down into three essential parts: a sign bit, is it positive or negative, the mantissa, those are the actual digits, and the exponent, which tells the computer where the decimal point is supposed to float to. Let's just quickly walk through a real example. Say you want to store a number like -3¼ First, the computer converts it to binary. Then it shuffles it around into that scientific notation format. And from there, it's easy. It just stores the three key pieces: one bit for the negative sign, a chunk of bits for the digits in the mantissa, and another chunk for the exponent. It's a three-part system for representing almost any number. But here's the catch, and it's a super important one. Because we only have a limited amount of space, a certain number of bits to store that mantissa, we can't always be perfectly precise. Sometimes you have to chop off the end of a really long decimal. This creates tiny, almost invisible, round-off errors. And that is why you sometimes see weird little graphical glitches in a video game, or why a big calculation in a spreadsheet is off by a tiny, tiny fraction. It's a direct side effect of how these numbers are stored. So we've built a system that can handle pretty much any number you can throw at it. For our last big jump, let's go from the world of math to the world of language. How do we teach a machine that only speaks in numbers how to understand words? The answer is, well, it's basically just a secret code, a beautifully simple one at that. A long time ago, a bunch of people just agreed that a specific number would represent a specific letter. This standard is called ASCII. So the number 65, or 01000001 in binary, will always be a capital A. The number 66 is always a B, and so on. Every single key you press on your keyboard is really just a shortcut for a number. It's honestly that simple. Now, ASCII was awesome for English, but for a global internet, not even close. It was way too small. That's why today, everything uses a much bigger system called Unicode. By using more bits for each character, it creates this massive library with over 65,000 slots. And that is what lets your computer show letters, emojis, and symbols from basically every language on Earth, all built on that same fundamental idea: one character equals one number. And this whole journey, from a simple on-off switch all the way to representing the whole of human language, leaves us with one last really fascinating question. We taught these machines how to speak our language by translating it into numbers. As we move into the future of AI and everything else, what's the next language we're going to teach them? What new, incredible concepts are we going to translate into the simple, powerful world of ones and zeros?